So the chapter 4 homework is due on Wednesday, the 29th. The quiz for chapter 4 was today. You should have just finished it. The chapter 5 homework will be due on the 12th of November. And the exam for chapters 3 and 4 will be on Wednesday, the 29th. So on Wednesday this week. So on Wednesday, we will not be having a lab. We will be having the exam. You get one sheet of notes. A calculator will be required. It's similar in length to the last exam. And there's no lab next week. But if you need to make up any labs, you can come in and make up labs then. So continuing on with chapter 5. Click. So we talked about specific heat. Specific heat is the heat required to warm up a substance when it's not going through a phase change. So specific heat, or specific heat, the heat required is going to be mass times the specific heat capacity, C, times the change in temperature. So different substances require different amounts of heat to warm up. The heat capacity, C, is the heat required to warm 1 kilogram of the substance 1 degree Celsius.
I'm sorry, no lab this and next week, or
no labs this week when we have the test. Next week we will have it.
okay, I'm misunderstood. Sorry.
Sorry, when we have the test this week, there's no lab. There's no lab when we have the test. That's the general structure.
Okay.
No, we have a heat lab that we'll do next week.
Okay.
So specific heat, that's the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So, wait, these are last week. I'm pretty. We should not be out of it. Yeah. Well, nobody took it, so that's good. That's right. Sorry. So that's specific heat. So in general, you're not going to need to know the specific heat of substances. The only one that you might keep in mind is that the specific heat of water is 1 calorie per gram degree Celsius, or 1 kilocalorie per kilogram degree Celsius. So specific heat is mass times heat capacity times change in temperature. And this applies to a substance that does not undergo a phase change. And for specific heat, you do need to keep track of the units. So for example, if the unit is given in joules per kilogram degree Celsius, it'll be joules. Given in calories per gram degree Celsius, you sort of have to keep track of that. Trying to remember what. Oh, that's on a future quiz or exam, so I can check to make sure that makes sense. Latent heat. So specific heat is what you use for warming up or cooling down something when it is not going through a phase change, not melting or boiling, something like that. If it is going through a phase change, melting, boiling, freezing, condensing, then you use latent heat. So for latent heat, heat required is mass times latent heat of, say, fusion, or mass times latent heat of vaporization. So as an example, I could do an example, I guess. So we will. That's bad. Luckily it didn't break, but I need to clean this up. I just spilled water all over the place. Like an idiot. These are absorbent. Was going to demonstrate a phase change. So I will demonstrate a phase change with a small amount of water. Okay, now so hopefully pretty soon. So right now, this water is warming up. So this would be specific heat. But so that's specific heat, and eventually it'll start to boil, and that will be latent heat. And if you look at the thermometer while it is heating up, and when it's boiling, it's going to sit at 100 degrees, even though I'm constantly adding heat with the Bunsen burner. So when a pot of water gets heated to 100 degrees, some of the water begins to change to steam. And as heat continues to be added, more water will turn to steam, but the temperature of the water will remain at 100 degrees Celsius. So where does this additional heat go? Basically, this heat goes into breaking the bonds between the molecules and separating the molecules into the different phases, and the transitions depend on temperature and pressure, which you can see via a phase diagram. So during a phase change, for example, from liquid to gas, which we're not at yet, getting there. The heat energy needs to be used to separate molecules rather than add to their kinetic energy. So it is latent or hidden heat. Basically, it goes into potential energy instead of kinetic energy. The latent heat of fusion occurs at the melting freezing point. It's the amount of heat required to change 1 kilogram of a substance from solid to liquid at the melting point temperature. The latent heat of fusion for water is 80 kilocalories per kilogram. The latent heat of vaporization is the amount of heat required to change 1 kilogram of a substance from liquid to gas at the boiling point temperature. It occurs at the boiling point. The latent heat of vaporization for water is 540 kilocalories per kilogram. So now let's talk about how heat transfer occurs. There's 3 main ways that we have heat transfer occur: conduction, convection, and radiation. And actually, probably all 3 are happening right here as I'm heating this. Conduction is how say heat is being transferred from the walls of the beaker to the water. As the beaker gets hot, the water gets hot, just through direct contact. That's conduction. It's also how heat is being transferred from, say, this wire mesh to the beaker. So conduction is just hot thing touches up, not hot thing, heat flows from one to the other. Convection involves the movement of a fluid. So here you can sort of think that there's this rising warm material underneath, that's convection. Or in the boiling water here, you can see there's rising hot water rising up to the surface. That's also a convection process. So convection involves the movement of a fluid. So in your car, the way your heater in a car works is it blows hot air over your engine, and that hot air moves through your car to warm your car up. That is convection. So if you've used a convection oven or an air fryer, those use convection to cook food faster by having a fan to blow the air around so the hot air moves around faster and can transfer heat more. And the last form of heat transfer is radiation. Anything with a temperature emits electromagnetic radiation. So this, part of why this gas is burning blue. So actually, this is well mixed, but if I futz with it, I can make it actually. So the yellow in the flame, that yellow is actually radiation heating. There's little soot particles in there of carbon, and those are heated up and glowing yellow. It's also, if you old-fashioned incandescent light bulb, it's just a hot wire. And here you can see, this is just sitting at a constant temperature as it boils. Temperature is not going up anymore, just staying steady. Well, I'm probably going to turn this off soon, just because I don't want to boil it dry. So those are the three methods that heat can be transferred. So conduction is transfer of heat by molecular collision. It's when things are touching. So how well a substance conducts depends on its molecular bonding. So metals conduct heat very well, which is why they feel cold. So like if you touch the faucet here, it's actually the same temperature as the desk. But if you touch the faucet or one of the metal things around here, it'll feel colder than the wooden desk, because this will pull heat away from your hands better than the desk will, because it conducts heat better. So thermal conductivity is a measure of a substance's ability to conduct heat. Things that conduct well tend to be things like metals. We use them when we want to transfer heat. If you've ever built a computer, you may have used thermal paste, which is goo that conducts heat very well because you want to cool your chips down. I'm going to turn this off. Insulation, on the other hand, insulation is designed to have very bad thermal conductivity. So liquids and gases are generally poor thermal conductors, poor insulators, because their molecules are further apart, particularly gases. Metals are generally good thermal conductors because their molecules are close together, and also because they have free electrons bouncing around, which can carry heat. So the thing that makes metals good electrical conductors also makes them good heat conductors. That's not always the case, but in the case of most metals, it's a similar sort of thing. Convection is the transfer of heat by the movement of a substance or mass from one position to another. So for convection to occur, something has to move. This building is heated by convection. There's a heater somewhere and they blow hot air out into the various rooms. Most homes are heated by convection. You have a furnace that you pump it, force air through, or other things like that. Just in general, most home heating methods boil down to convection. To stop convection, to insulate against convection, air is a terrible conductor of heat, but it moves around easily, so it's good at convection. So if you want an insulator, you want your air to not move. So what you do is you trap it in a foam or in downy feathers or whatever. You trap air, and that provides convection, insulation. And radiation is the one that's hardest to stop. The process of transferring energy by means of electromagnetic waves. Electromagnetic waves carry energy even through a vacuum. In general, darker objects like this will absorb radiation well, and light-colored objects reflect radiation, so they don't absorb radiation well. So if you want to reduce cooling from radiation, you tend to basically put mirrors on things, because it's just light. The radiation in question is light. So for something that's designed to stop all forms of heat transfer, so good insulating material generally has an abundance of open airspace to inhibit the movement of heat, but it's also set up in such a way that that air can't move. So like goose down sleeping bags or spun fiberglass for house insulation, pot holders, which are fabric with batting. So there's layers, there's gaps in there. Double pane windows, where the gap between the two panes has the air actually pumped out and replaced with a small amount of a different gas that's even less good at transferring heat. So that's how double pane windows work to be good insulators. So yeah, the best insulator is nothing, literally nothing. If you could if you can make a vacuum, you can't have conduction and you can't have convection, because there's nothing there to conduct, there's nothing there to carry it around to convect. So a vacuum flask or a thermos, as you may have heard, or I mean, this is a modification of that. Like if you've got one of those double-walled insulated cups like this, uses all three principles. The best ones are made of glass, because glass is a cruddy, not a very good conductor. They have a silvered surface on the inside to reflect back radiation, and a vacuum in between the layers. So this stops the transfer of all three forms of heat energy. The partial vacuum between the double walls kills conduction and convection, because there's nothing there to conduct and there's nothing there to convect. The silvered inner surface of the inner glass container minimizes heat transfer by radiation. Thus, a quality thermos bottle or a vacuum bottle is designed to either keep cold foods cold or hot foods hot. And when you want to do seriously low or low temperatures, you use what's called a Dewar flask, which is sort of a bigger version of that. And what you can do is it's the same thing. They shouldn't be made of metal though, because to be stronger. But you have a vacuum gap in between, and for the best ones dealing with the coldest temperatures, they actually often have layers of like foil reflectors on the inside to bounce back even more of the radiated heat. I did low temperature physics, so we had a big Dewar that we used, filled full of liquid helium, and had to keep it cold. So the phases of matter, the three common phases of matter are solid, liquid, and gas. We put this away so we don't break anything, and I included hungry things. And pressure and temperature determine in which phase a substance is. So some examples at normal room pressure and temperature. Copper is solid. So copper is solid, or this is mostly copper. I don't know what that is exactly, but it's mostly copper. Water is a liquid, and oxygen is a gas. So all three of those are, you can see all three of those like in front of you. Those are some examples. That's it. Normal room pressure and temperature. If you want to cause something to go from one phase to another, you can change the pressure or the temperature. Generally, as you warm things up, things will go from solid to liquid to gas, so sometimes they'll skip liquid or such. And as you increase pressure, things will go from gas to liquid to solid. Though again, it can vary depending on the particular pressure you have. So here is a phase diagram. This shows what happens for all phases of a substance, at all pressures and temperatures. So this is the phase diagram for water. Here we have down here, this is a gas. So low pressure, high temperature, that's a gas, generally. And here we have a liquid, which is sort of in the middle. And then here at high pressure, low temperature, we have solid. And water has a billion different types of solid. There's more that are even on this chart. I think they're up to like 21 now. I think I saw something about a new form of ice. But so generally, as you eat, so temperature is this way, pressure is this way. So this red line here is normal atmospheric pressure. So this is, this is about where we are. You warm up water, it boils. You cool down water, it freezes. But you can also do pressure. If you lower the pressure of water, it will boil. If you increase the pressure of water a lot, it will become solid. And there's also this critical point. So this here is the critical point. Beyond the critical point, you get into sort of a fuzzy region where the difference between liquid and gas isn't really. So beyond the critical point, instead of a sharp transition from liquid to gas, it's a gradual transition. It's fuzzy in that, beyond that point. So there's some interesting things you can do with that. You can use what's called the supercritical fluid, which will act like both a liquid and a gas. And it's really useful for sort of dissolving things, but then removing things easily from substances, because as a supercritical, because it'll act more like a gas than a liquid. So you can dissolve things in it and then carry those things out very easily. It's actually used for dry cleaning. So one of the new methods of dry cleaning uses supercritical CO2. But there's some interesting things you can do with supercritical fluids. You can also use them to make things like aerogels. But yeah, so this is a phase diagram for water. So here's the sort of different phases. In solids, the molecules vibrate. They don't really move very far. They vibrate back and forth in their position. Solids have a definite shape and volume. So, this is a solid. It's not taking the shape of its container. It's not changing volume. Solids come in two types. There are crystalline solids. Most minerals are crystalline solids. So, this aluminum is a crystalline solid. This, I think this is iron, is a crystalline solid. Most solids are crystalline solids. The molecules are arranged in a particular repeating pattern. When you heat them up, the molecules will gain kinetic energy. They'll vibrate more. This will cause the solid to expand because it's jiggling more and it sort of stretches everything out. But they have a repeating pattern. There are also amorphous solids. Amorphous solids lack an ordered molecular structure. So amorphous solids will not suddenly melt at a specific temperature. They just gradually become softer, and there's no definite melting temperature. An example of an amorphous solid is glass. So the classic amorphous solids are, another term for an amorphous solid is a glass or glassy. And one of the ways you can make an amorphous solid is cool down something so fast it doesn't have time to order itself. So that's how you get things like obsidian, which is volcanic rock that cooled down so fast it didn't have time to get ordered. So in a crystalline solid, you have an ordered lattice. A crystalline 3D orderly arrangement of atoms called a lattice looks like this. And if you increase the temperature, the lattice will expand. Now, they're not always square like this. There are different patterns, like ice is hexagonal. There are different crystal structures that depend on what atoms this is made of. But square, cubic like this is pretty common. So here's an example of something with a cubic lattice. Table salt, NaCl, is cubic in its lattice structure. In a liquid, the molecules can move and assume the shape of their container. So I have my container here. The volume of the liquid doesn't change, but as I move the container, the shape of the liquid changes. Definitely some solid particles in this liquid. The liquid has little or no lattice arrangement. It has a definite volume, but no definite shape. The shape can change, but the volume doesn't. And liquids expand when they're heated because the molecules move around more until you hit the boiling point, when the molecules can break free and fly off on their own. And then you get a gas. So a gas or a vapor, when the heat is sufficient to break the individual molecules apart from each other. So if you have a liquid, you have all these molecules that sort of attracted to each other, but they're not in any bound structure. They can flow around and move around. If you get them hot enough, they'll literally just break free. And that's a gas. So when the heat's sufficient to break the individual molecules apart from each other, you get the gaseous phase. The gaseous phase is reached when the molecules are completely free from each other, and they just bounce around and bounce off each other. And because of this, it means that gases are kind of the simplest phase. Gases will assume the entire size and shape of their container. For example, I can fill this container up with gas. If I squeeze it or compress it, it will get smaller. The pressure, volume, and temperature are all very closely related in gas. So gases are all very close. You can approximate a gas by just like freely flying balls bouncing around, kind of. So there's something called the ideal gas law, and it'll deal with the relationship between pressure, volume, and temperature in gases. And it works because the particles in gases are so far apart, they basically barely interact with each other. They just bounce off the walls and bounce off each other. There are some exceptions. The big one is steam, especially steam close to 100 degrees Celsius. Water has a lot of intermolecular forces, and so steam is sort of irregular. Now, if you heat a gas up enough, you can actually rip the electrons off of the molecule of the atoms in the gas and ionize it. The molecules and atoms will be ripped apart due to the extreme kinetic energy, and you end up with what's called a plasma. So plasmas exist inside our sun and other very hot stars, but if you've ever seen a spark, that's also a plasma. And you can make plasmas at lower temperatures. Generally, you need to do it at lower pressures. But if you've ever touched one of those like globes where you get weird lightning bolts to your fingers or something like that, that's a plasma. So plasmas exist in our sun and other stars. The ionosphere of the Earth's outer atmosphere is a plasma, and plasma is considered another phase of matter. There are several other phases of matter as well. Like, the one I was studying was superfluids. You get something cold enough, fluids can start to act very strangely. So let's talk about gases. So the kinetic theory of gases is that a gas consists of molecules moving independently in all directions at high speeds. So you basically use Newton's second law. You just use Newtonian mechanics, and you can actually build up from there to get a model of gases. And the idea is that the higher the temperature, the higher the average speed of the molecules. The gas molecules will collide with each other at the walls of the container. And the distance between molecules is on average large compared to the molecules themselves. So this basically, if you could actually derive this reasonable approximation of how gases work by assuming gas molecules don't interact with each other and they just bounce off the walls of the container there. So the result of the collisions of billions of gas molecules on the walls of a container, like a balloon or a ball, is pressure. So I have a balloon. It's got some gas in it. Those are bouncing around. They're pushing out and stretching the rubber. If I add more gas molecules, I get more collisions, thus a higher pressure. If I have less collisions, thus less pressure. So more gas molecules means more collisions, more force on the container, therefore more pressure. Pressure is just force over area, and it's coming from various things bouncing off of this. So pressure is defined as force per unit area. The SI unit is a Newton per square meter. It's a Pascal. It is very small because a square meter is big and a Newton is not very big. A more commonly used unit of pressure that is based off the SI system is the bar, which is based off the old CGS system. But the bar is 1 times 10 to the 5th pascals, and it has the advantage of being very close to atmospheric pressure. Atmospheric pressure is 1.013 bars, something like that. And, atmospheric pressure actually varies, but it varies between like 950 millibars to 1050 millibars, something like that range. Now, another common unit is the atmosphere. 1 atmosphere is normal atmospheric pressure at sea level and 0 degrees Celsius. 1 atmosphere is 1.013 times 10 to the 5th pascals, or 14.7 pounds per square inch. You are currently feeling 1 atmosphere of pressure from the atmosphere, or about that. Might be a bit more. I have a barometer over here, but I don't think it's calibrated right. So this reads high. it's a little bit more than 1 atmosphere. Now, 1 atmosphere is about 1.13. I suspect it's about 1.20. Currently. I mean, you can look it up, it's in the weather. And here's an example of force, pressure, and area illustrated. So if you've ever used a thumbtack or a knife, that's a tool to increase pressure by decreasing area. So the idea is with the thumbtack, your thumb applies force over a large area, but the sharp point transfers that force over a much smaller area, leading to a much higher pressure. So the relationship between pressure and the number of molecules. So if the temperature and the volume are held constant, pressure will be directly proportional to the number of molecules. The pressure is proportional to the number of molecules. I should be doing this with an easier. Proportional to the number of molecules. The pressure is directly proportional to the number of molecules. Double the number of molecules, double the pressure. If volume and number of molecules are held constant, pressure is directly proportional to the Kelvin temperature. So it's directly proportional to temperature, but that temperature has to be an absolute temperature scale. So it has to measure temperature starting at absolute zero. So like Kelvin, or there's an equivalent one for Fahrenheit. It's like Ratkin or something. I can never remember the name. But Kelvin temperature. So whenever you're doing problems about gas law, you'll have to convert to Kelvin if they give temperatures in Celsius. I believe there's at least one problem on your homework like that. And then lastly, if temperature and number of molecules are held constant, pressure and volume are inversely proportional. If you squeeze your gas down into a smaller container, the pressure goes up. So if you have the volume of your container, you will double the pressure. You can think of it as it takes less time for the molecules to hit the walls, to go from one side to the other, so they hit more often, so the pressure goes up. If you increase the number of molecules, you increase the number of molecules bouncing off the walls, that increases the pressure. If you increase the temperature, the molecules are moving faster, so they hit harder, that increases the pressure. If you decrease the volume, it takes less time to hit the walls, so that increases the pressure. So we find that pressure is proportional to Nt over V, directly proportional to the number of molecules and the temperature in Kelvin, and inversely proportional to volume. So we can write a relationship with ratios. P2 over P1 equals V1 over V2 times T2 over T1 times N2 over N1. So this is giving you the version with N constant. All the problems you will have to do will have N constant, but the more general form, you can add N as just another term here. If N is constant, this goes to 1. If something is constant on this, their term goes to 1. Because something divided by itself is just the same. And it turns out this relationship, this proportionality here, this can be identified, compressed into an actual general equation. There's a constant that relates them. So the full form of the ideal gas law, the most commonly used version is PV equals little m big R T. That's the one generally used by chemists. This is the number of moles of a substance, pressure, volume, temperature, number of moles, and this is what's known as the gas constant. There's another version of this that gets used by physicists sometimes, which is PV equals N K Boltzmann T. Well, this is the number of particles, and this is what's called Boltzmann's constant. And physicists like to use this version because this corresponds to like energy per particle. So it's useful because that KBT term shows up a lot. That's all. Now you don't actually need to know the ideal gas law. I'm not going to actually give you any of the constants for it because all the problems we have you can just do with the ratios. I just wanted to show you it. But these are the same thing. This is the total number of molecules. This is the number of moles of molecules. So there's just a factor of Avogadro's number there. So that means to go from Boltzmann's constant to the gas constant, there's just a factor of Avogadro's number. They're just different ways of expressing it. It's just often more convenient for practical terms to talk about moles of a substance because you can measure them more easily. And 1 mole of a substance is like a reasonable amount of stuff, like a mole of hydrogen. Oh no, like a mole of oxygen. A mole of oxygen weighs about 16 grams. But it's also like 6 times 10 to the 23rd particles. So capital N here ends up being a really big and kind of awkward number. So here's an example. If you have a closed rigid container, closed means N is fixed, rigid means volume is fixed. Holds a particular amount of hydrogen gas. The initial pressure is 1.8 times 10 to the 6 pascals at 20 degrees Celsius. What will the pressure be at 40 degrees Celsius? So given V1 equals V2, it's a rigid container, times pressure 1, T1, T2. We need to convert T1 and T2 to Kelvin and add, so we'll add 273 degrees. So 20 degrees Celsius is 293 Kelvin. 40 degrees Celsius is 313 Kelvin. So P2 over P1 equals T2 over T1 because the volume term goes away because it's constant. So P2 will just equal temperature 2 over temperature 1 times P1, or 313 Kelvin divided by 293 Kelvin times the initial pressure of 1.8 times 10 to the 6 pascals. And so the final pressure will be 1.92 times 10 to the 6 pascals. And this is an increase like we would expect. So that indicates we didn't make a horrible mistake here. And I think I'm going to stop there. We'll go over this again next time after the test. Remember, we have the test on Wednesday. There is not a lab. I'll see you all on Wednesday. Stop sharing.